Well, what if instead of making pancakes, we're making molecules? Not as tasty, but this is chemistry class. The balanced chemical equation is like the recipe for making this product. So here we have a recipe. 3 molecules of hydrogen will react with 1 molecule of nitrogen to form 2 molecules of ammonia. This equation also applies to moles of substances. We don't talk about individual atoms and molecules much because we never deal with that few particles. We can't even see them, right? So we deal with dozens, chemist dozens, called moles. The ratios are the same. Oops. So good grief. When we read this equation, we can say, well, 3 moles of hydrogen will react with 1 mole of nitrogen and make 2 moles of ammonia. We could do the same thing with that recipe and say, well, if I wanted 5 dozen pancakes, how many dozen eggs would I need? The same number in the recipe, right? 2 dozen. All I've done is multiplied everything by 12. So when I put mole in here instead of individual molecules, I'm just multiplying everything by Avogadro's number, which is a big, ginormous number. And so instead of using these huge numbers, we use this unit mole, and then everything is nice numbers. Okay? So everybody okay with 3 moles of this, 1 mole of that, and 2 moles of that? So we can form ratios from this chemical equation. We can actually form a whole bunch of them. So we can find a ratio between hydrogen and nitrogen. So we could say if we want moles of hydrogen and moles of nitrogen, the relationship between those. Well, it's 3 moles of hydrogen to 1 mole of nitrogen. We could look at moles of ammonia to moles of hydrogen. 2 moles of ammonia are formed from 3 moles of hydrogen. 2 moles of ammonia from 3 moles of hydrogen. You see what I'm doing? This is really important. Any questions? I can make a combination between any 2. I can make a ratio between 2 reactants, between a reactant and a product. If we had 2 products, I could go between those. You can put the product on top or the reactant on top. You can make any ratio you need from this balanced chemical equation. Okay with that? Same equation. If we have 3 moles of nitrogen and plenty of hydrogen, how much ammonia can we make? Well, you might be able to do this one in your head as well, but let's write it out. So we're starting with 3 moles of nitrogen. And we want to know how many moles of ammonia. So this is the unit we want, and we need to divide by this unit, moles of nitrogen, so those units cancel out. After we figured out what the units are doing, we look at the equation and we see that for every 1 mole of nitrogen, we can make 2 moles of ammonia. So I'm going to put 2 in front of moles of ammonia and 1 in front of moles of nitrogen. And then it's just some math, and it's 6 moles of ammonia. Any questions? That one had nice small whole numbers in it, but oftentimes they're not nice small whole numbers. So let's look at this example. How many moles of nitrogen are needed to completely react with 7.13 moles of hydrogen? So this number's a little messy. Same process. 7.13 moles of hydrogen. And what we want to know is how many moles of nitrogen would we need to completely use up that hydrogen. So this is what I'm trying to get, and then I'm going to divide by this unit, moles of hydrogen. Where do I get the units for this? From the equation, these coefficients. So in front of nitrogen is an understood 1, and in front of hydrogen is a 3. So I put a 3 in front of hydrogen. So I need my calculator for this one because I can't do that in my head. 7.13 times 1 divided by 3. And the unit is moles of nitrogen. These numbers, the coefficients in this equation, are exact numbers because they come from looking at individual atoms and molecules. So they are exact. So that's not going to affect our sig figs. This, we start with 3, so we're going to end with 3, and so our best answer would be 2.38 moles of nitrogen. Any questions? Let's do another example. So, water forms when hydrogen gas reacts explosively with oxygen gas according to this balanced equation. How many moles of water result from the complete reaction of 24.6 moles of oxygen? Assume there's more than enough hydrogen. So we're given this equation. The sentence at the top, that's just fluff. That's just words. The chemical equation here is what we need. And this number, we need to know what unit we're starting with and what unit we're ending up with. I like to use the balanced chemical equation to organize the information. So 24.6 moles of oxygen. I'm going to write that under oxygen. So 24.6 moles of that. And the question says, how many moles of water? So the question is, how many moles of water, question mark, moles. And now I've got a more visual representation of what I'm doing. I start with the number and I end with the question mark. So this, if we want to write out a path, and some of you really still need to write out a path, we're starting with moles of oxygen and we're trying to get to moles of water. So our starting point is the number of moles of oxygen, 24.6 moles of oxygen. One arrow, one factor. Moles of water on the top, moles of oxygen on the bottom. My path tells me what goes in the numerator. Moles of oxygen to moles of water. Moles of oxygen to moles of water. I put moles of oxygen down here because I need this unit to cancel out. So those units go away and I'm left with the unit I want. I need numbers in this relationship. They come from the balanced chemical equation. In front of oxygen is an understood 1. I'm going to put a 1 down there. In front of H2O is a 2. So I put a 2 here. So you do the math and you come up with 49.2 moles of water. This had 3 sig figs, that has 3 sig figs. Any questions? This chapter is the biggest reason that you needed to learn dimensional analysis. If you know dimensional analysis, this is one small step. If you don't understand dimensional analysis, this is going to be a mess. I'm not going to say it's impossible, but it's going to be more difficult.